Alright, so this is the beginning of chapter 6, which is called the integral. And 6.1 is called the indefinite integral. Okay. So we're now moving into the second part of calculus. If calculus could be split into two sections, you could say there's differential calculus and integral calculus. So differential calculus, the main operation, differential calculus, as its name implies, the main operation is derivatives. And for integral calculus, the main operation is integration. And that's what we're going to start looking at today, integration. I'm going to follow the approach the book takes here, where I first introduce the integral as the sort of an inverse operation of a derivative, and I'm not going to look at the geometric interpretation of the integral until section 6.3, even though it's a really nice interpretation and super important, but for now I'll follow the approach the book takes, and I'll just kind of sweep all of that under the rug and just tell you that first definition, an antiderivative. So we're kind of going to be talking about integrals as antiderivatives, sort of the inverse operation of a derivative. So antiderivative of a function f is another function, we'll call it usually capital F, so that f is equal to f prime. Little f is equal to cap f prime, capital F prime. So in other words, or I should say the antiderivative of a function little f is a function capital F, so that little f is equal to big F prime. So for example, if I know that, let's say some function, let's see, I don't want to get confused here about the notation. If f of x is equal to x squared, then we need a function capital F so that f prime is equal to x squared. So that f prime is equal to x squared. And this is kind of the name of the game for integration. You're trying to think of, and we're going to define rules that make this easier in a little bit, but you're trying to think backwards, trying to think of a function so that when you take its derivative, you get x squared. You get x squared. So what could f be? What could capital F be here? So try to think, pause the video and see if you can figure out, just write down a function, take its derivative, so you can remember how the power rule works, and then think of a function so that when you take its derivative, you're going to get x squared as the result. So you may be thinking, capital F needs to definitely have a power of 3, so that when we decrease the power by 1, we'll have x squared. But if I take the derivative of this, I'll have 3x squared, right? But I want just x squared. So it's close, but it's off by a coefficient, that coefficient of 3. But if I add a factor of 1 over 3 here, now when I take the derivative of this, I'm getting that capital F prime, drop the 3, lower the exponent by 1, and then the 3's cancel, and I'm left with x squared. So this is what an antiderivative is. It's a function so that when you take the derivative of it, it's equal to the original function. The antiderivative of the original function is some other function so that when you take the derivative of the other function, you get the original function. And by the way, all of these are functions of x. I just kind of suppressed that notation, but all of these are functions of x. Okay. Let's do another example. Just some short little examples, because we're actually going to define some rules that will make finding antiderivatives easier. So let's do examples. With antiderivatives. Okay, so think of an antiderivative for 4x cubed. Think of an antiderivative of 4x cubed. So some function so that when you take its derivative, you get a result of 4x cubed. So we're thinking in reverse here, an antiderivative. So what if I take the derivative of x to the fourth? Take the derivative of x to the fourth. Well, x to the fourth prime is going to be, drop the 4, lower the exponent by 1 is 4x cubed, so x to the fourth works. Okay. What about another one, 4x cubed, but couldn't I say x to the fourth plus some number like 7? What is the derivative? Is this still a legitimate response? Oops, 7. Is this still a legitimate answer for the antiderivative of 4x cubed? Well, what is the derivative of x to the fourth plus 7? It's still 4x cubed, because the 7 goes away, right? Derivative of a constant is 0. So this is also a legitimate answer. In fact, for the function 4x cubed, there is a whole collection of functions that are antiderivatives of 4x cubed. The collection is defined by x to the fourth plus some constant, and we usually say c for the constant, where c is a constant, is a real number. If I wanted to be specific, c is a real number. Okay, so that goes for could be x to the fourth plus 7, x to the fourth plus 1, x to the fourth minus 45. If it's a constant, then this is a legitimate antiderivative. What about x squared? No, let's do 2x. Let's do 2x. What is a possible antiderivative for 2x? Well, what function do I take a derivative of to get 2x? X squared, right? Because if I take the derivative of x squared, I drop the 2 up front and take the exponent down by 1, and I'll be left with 2x. So I could say x squared plus 83. This would be any constant. X squared plus any plus or minus any constant. So by the way, c is a constant here, a real number. C can be negative. C can be negative. So if I wanted to list all of them, this is just one example of an antiderivative of 2x. But if I wanted all of them, I would say this, x squared plus c. Let's see. Okay. Okay. So we call this set the set of all antiderivatives, because remember, this is not one antiderivative here. This is a set. This is infinitely many. This is a whole set of antiderivatives. This is one particular antiderivative. This is the entire set. We call that set of antiderivatives for a function the set of all antiderivatives for a function the indefinite integral. Indefinite integral of the function. Okay. We denote the indefinite integral by what looks like a giant S. That's an integral sign. And you write the function that you want to find the antiderivatives for, and then dx. And this notation is not going to make any sense until we talk about the geometric interpretation of an integral. And I really want to talk about it now, but I'm going to stick with the approach of the book and just put it off for later. Okay. So this is read as, this is the indefinite integral of the function f of x with respect to x. This is the set of all antiderivatives. The indefinite integral of a function is the set of all antiderivatives for that function. And when I say with respect to x, that's what this part is telling you. It actually means a lot more. The little dx is actually super important. For now, think of it as sort of closing the operation of integration here. So this is where the operation starts, and this is where it ends. And it also tells you what variable you're taking, you're investigating here, which it'll always match whatever the variable is for the function. It doesn't have to. For us it will, though, at least in the beginning. I'm not going to give you a function of t and ask you to take its indefinite integral with respect to x, at least not yet, not while we're still learning the operation. So let's do some practice just with this notation. So, let's say example with notation, indefinite integral notation, indefinite integral of f of x with respect to x notation. Let's say check the following. So right now we don't have any explicit rules for finding the indefinite integral. It's still just kind of like implicitly defined with derivatives. I say, so far all I've told you is if you want to find this, you need to think backwards about, what derivative or what function do I take a derivative of to get this, and that's tough. That's hard to do, especially if you're, not comfortable with differentiation. Then thinking of it backwards is really tricky. So in this problem, all I'm going to ask you to do is confirm that this is the collection of antiderivatives for this function x. So f of x here is just x. So the way you check this is you take the derivative, of this function, of this output here, and see if you get x. So drop the 2, have 2x over 2, just taking a derivative. This is just a derivative. Plus c goes away, and I'm getting just x there. 2's cancel, I'm just getting x. So this is a legitimate indefinite integral for the function x. So what I'm doing here is I'm giving you the solution and asking you to check it by taking the derivative. Okay, so we want to confirm that this is the collection of antiderivatives for x squared. So I'll take the derivative, and I'm getting, let's see, drop the 3, the 3's will cancel, the c goes away, the constant goes away, and I am in fact just left with x squared. Okay. What about six x to the 5th dx? Integral of 6x to the 5th dx is equal to x to the 6th. Plus c. Okay, so we take the derivative of x to the 6th plus c. C is just going to go away, right? So we can basically ignore it. Drop the 6 as a coefficient, take the exponent down by 1. Okay, so we get 6x to the 5th, which matches here. Let's do some more interesting ones now. How about integral of x to the negative 1 dx equal to ln of absolute value of x plus c? Well, taking the derivative of ln of x plus c, ln of absolute value of x plus c. The absolute values are just there because over here, the domain of x to the negative 1 only has one restriction. It just can't be 0. But it can be negative and it can be positive. But this function, ln of x, can only accept positives. That's why we have absolute value around it. Because if I plug in a negative 2 over here, that's a legitimate input over here, but not a legitimate input over here. So I restrict the domain of this function over here to just be absolute values. It's just a detail. It's just something that's necessary and important, but not something to worry too much about. When I take the derivative of this, I know the c doesn't matter. And ln of absolute value of x, well, ln of x, the derivative of ln of x, we learned, is 1 over x, right? So 1 over x. So just kind of sweeping this absolute value business under the table, or under the rug, whatever the saying is. I'm getting 1 over x, which is exactly x to the negative 1. What about just integral of a number? And I'm saying that integral of 2 dx gives me 2x plus c. Well, what is the integral of 2x plus c? Or sorry, derivative. What is the derivative of 2x plus c? The derivative. Well, it's just 2, right? X goes away, the c goes away, we're just left with 2. We're just left with 2, which is exactly what is in the input of the integral. What about integral of square root of x dx equal to, this is a bit different, 2/3 x to the 3/2 plus c. Well, take the derivative of this side and see if we get square root of x. And remember that square root of x is x to the 1/2. So derivative of 2/3 x to the 3/2, oh, plus c, whoops, plus c prime. Okay, drop the 3/2 down as a coefficient, so 2/3 is there times 3/2 times x, and then the exponent of x is going to become taken down by 1, so taking 1 away from 3/2 leaves me with 1/2, and the plus c goes away, so I'm left with just x to the 1/2, which is exactly square root of x. See how the 2/3 and 3/2 canceled each other out. So 2's and 3's cancel. I've got a couple more. Number 7. Number 7 says integral of 2 to to the x, so an exponential function, dx, is equal to 1 over ln of 2 times 2x plus c. Okay. Now, we know that just recall, I'll actually recall this derivative rule since it's fairly new. The derivative rule for an exponential function is if you've got some exponential function b to the x prime, that's going to be ln of the base times b to the x, just like that. We're seeing kind of the opposite here, though, right? So it's 1 over ln of the base instead of just times ln of the base. So what's going on here? Well, if we take the derivative of this right-hand side, 1 over ln of 2 times 2 to the x plus c, we're supposed to get 2 to the x. And maybe you're seeing now why the ln of 2 has to be in the bottom here. Because what's the derivative of this? Well, 1 over ln of 2 is just a constant that's attached by multiplication to the function of x, so it just gets carried along. Whereas plus c is a constant attached by addition, so it just gets dropped. Now, what's the derivative of 2 to the x? Well, it's ln of 2 times 2 to the x, and you see how these will and you see how these will cancel, leaving me with 2 to the x. Okay. So hopefully you're seeing how the indefinite integral of a function is really the opposite of taking its derivative. If the derivative of 2 to the x is ln of 2 times 2 to the x, then the antiderivative of 2 to the x is 1 over ln of 2 times 2 to the x. Alright, last one here. Let's say integral of e to the x dx is equal to e to the x plus c. So take the derivative of e to the x plus c, see what we get. Well, derivative of e to the x is just itself, and the c goes away, and there we go. So e to the x is just as nicely behaved for integration as it is for differentiation. It's a very nicely behaved function when it comes to taking derivatives and integrals. Alright, now let's actually get a rule in place for taking indefinite integrals. First rule we learned for differentiation was the power rule. And that's going to be the first rule we learned for integration as well. The power rule for integration says that if you... Now, let's recall just over here, the power rule for differentiation, for derivatives, you drop the n down, you multiply by n, whatever the power is, you multiply by it, then you take the exponent down by 1, just like that. We're going to do the opposite over here. So if I have the integral of x to the n dx, so the integral, I'm going to do the opposite. I'm going to, in the opposite order too, I'm going to add 1 to the exponent. So instead of n minus 1, it's going to be x to the n plus 1. And instead of multiplying by the old exponent here was n, right? Now I'm going to divide by that new exponent. There it is. Oh, n plus c, right? Plus c. This can also be written as 1 over n plus 1 times x to the n plus 1 plus c. And by the way, n cannot be negative 1 here, right? Because if n is negative 1, then we get a domain error, right? But we already figured out what the x to the negative 1 antiderivative is somewhere. Where did we do that one? There it is. The antiderivative of x to the negative 1 is ln of x. The whole collection of antiderivatives of x to the negative 1 is ln of x plus c. I should say ln of absolute value of x plus c. So this is a very special case. But for every other exponent besides -1, this is the rule. For polynomials and rational functions and radical functions. Not for exponential functions. Separate rules for these guys and these guys. Okay. So just as, let me just reiterate the point about the special case here. X to the -1 dx is equal to ln of absolute value of x, which can also be written as 1 over x dx, right? These are the same. Okay, so let me keep that power rule there. And let's do some examples. Okay. Examples. With the power rule. Okay. Let's take the indefinite integral of x to the 32nd dx. So I keep saying indefinite integral because that is what we're defining here. That's the operation we're working with. There is such a thing as the definite integral, and we'll talk about that in 6.3. Okay. X to the 32nd. So n here is 32. N is 32 here. So now I'm not giving you the solution and asking you to confirm by taking the derivative. I'm actually asking you to take the indefinite, or to find the indefinite integral for x to the 32nd by using this rule that undoes the power rule for differentiation. This rule here. So it's going to be x to the 33rd, right, because n is 32, over 32 plus 1, so 33, and then plus c. See, not too bad, not too bad. Okay, how about 1 over x to the 42nd dx? By the way, sometimes this can be written as dx over x to the 42nd, just so you know. Just so you know. Okay. N here is not 42, right? It's negative 42. Gotta be careful there. If it's in the bottom, then if the x is in the denominator, then it's a rational function, right? And that 42 is negative if I write it as an exponent. So alternatively, I suppose another way of writing this integral is x to the negative 42 dx. And maybe this makes more sense to you. Maybe this is more helpful to write it this way. So if we use n equal to 42 here, then I'm going to have x raised to the negative 42 plus 1 is negative 41 over n plus 1 is negative 41. And if I get this cleaned up, I will have negative 1, forgot the plus c, and then there we go. Now I'll have negative 1 over 41. There's the negative 41 in the bottom, right? I'm just putting the negative sign up top. And then x to the 41, and then plus c. So this negative right here is there. And this 41 stays in the bottom because it's in the denominator, right? It doesn't go up to the top. And then x to the negative 41 is the same as 1 over x to the 41. So the only thing left in the top is just a 1, because this 41 is already in the bottom. This x goes to the bottom because of that negative exponent. So the only thing left up top is a 1, and I'm just storing this minus sign right there. And then the plus c, of course, just is hanging out. Okay, let's try number 3. This is an interesting one. How about integral of 1 dx? Just a 1. Or this can even be written as, if I suppress that 1, just integral of dx, which looks like like some kind of mistake, right? But it really is the same as integral of 1 dx. So what is going on here? Well, what's really going on, or the way I can think of it, is x to the 0 dx. X to the 0. Because anything to the 0 is 1, right? So x to the 0. So here n is equal to 0. This number, the n, is the exponent on the variable. So if I force a variable in here, then the exponent on the variable has to be 0. And then what does that mean? So what is integral of dx? Well, it's going to be x to the n plus 1, but n is 0, so just x to the first power, which is just x, over 0 plus 1, which is just 1, so still just x. X to the first power over 1, I guess I can write those, and then plus c, but really, this is just x to the 1 over 1, that's just x, so just x plus c. So I can say all of these things are equal to x plus c. So I can say integral of 1 dx is equal to integral of dx, or I could write it as integral of x to the 0 dx, but they're all equal to x plus c. These are just different notations for saying the same thing, and you possibly could come across all of them. Let's do a couple more. What is this, number 4? Number 4. Integral of 1 over square root of x dx. Well, I need to know the power on this. I need to know the exponent so that I can use my power rule, right? Isn't this the same as x to the negative 1/2, right? So you see, when I'm rewriting these integrals so that I can identify the exponent, I keep rewriting this giant s, elongated s symbol, and the dx. I'm not I'm not doing the operation yet. I'm just rewriting it so that I can apply this power rule. So now that I see n is equal to negative 1/2 for this problem, negative 1/2, now I can say, well, this is x to the n plus 1, n is negative 1/2, so negative 1/2 plus 1 is 1/2. And then over n plus 1, that's negative 1/2 plus 1, which again is 1/2, right? These should match. These should match. The new exponent should match down here. And then plus c, and this can surely be cleaned up to... Now, if I've got divided by 1/2, remember that's 2, right? And then x to the 1/2 plus c, and if I really wanted to, I could write this x to the 1/2 as a square root of x. Okay. Number 5 is integral of cube root of x. So that's a cube root, that's a little 3 there. But again, I need to know what this is as an exponent, and it's 1/3. It's 1/3 as an exponent. Okay, so now I'm going to apply my power rule for integration with n equal to 1/3. So I'm going to say x to the n plus 1, so what's 1/3 plus 1? Well, that's going to be 4/3. And then in the bottom I should have 4/3. And then plus c. So once you figure out the exponent, you've got that coefficient in the bottom. They should match, because they're both n plus 1. N plus 1, n plus 1. Now remember, if you've got a fraction in the denominator here, then that means you're going to write it up top and flip it over, just like I did with the 2 here. The 1/2, the 1 over 2 became a 2 over 1. And now the 4 over 3 will become a 3 over 4. And then I'll have x to the 4/3 plus c. And I can write that back in radical form. 3/4 times the cube root because the denominator of this exponent should match the root, the index of the root, and underneath should be x to the fourth, and then my plus c out here. And yes, this can be simplified if this 4 under here is triggering your pre-calculus, you want to pull this one x out of this. That's possible, but you don't need to worry about it. In fact, for doing the operations of differentiation and integration, it's more helpful to have all your x's packed into one with one exponent. That's really the best way of writing them, all with one exponent. Instead of having like a whole x and a third of an x, just have them all in the same place so that you can do the operation all at once. Alright, one more. Integral of 1 over cube root of x dx. Again, this is not explicitly written with its exponent, right? It's written in radical form. So I need to write this as integral of x to the 1/3 dx, but it's not just 1/3, because it's not the same as this function. It's 1 over, right? So that's a negative exponent, negative 1/3. So my n here is negative 1/3. So I'm going to have x to the negative 1/3 plus 1. That'll give me x to the 2/3. And then over 2/3, because these should match again, and then plus c. And that will give me 3/2. Remember, if it's a fraction in the denominator, you flip it, and then x to the 2/3. You don't flip that exponent. That's that fraction. That's the exponent of the x. So you don't mess with that. The only time, plus c. The only time you mess with it is if you want to write it back in radical form. So I can say 3/2 times the cube root of x squared plus c. So either of these would be fine. Okay, that is the power rule for integration. Oh, I know. Let's do one more. Let's do one more before I'm getting out of here. Actually, just as a separate problem, let's prove the power rule. And this will be a very quick proof, not a very technical proof. We're just going to take the derivative of, just like we were proving these back here when I was asking you to confirm these, all of these problems, examples with this notation, just confirming by taking the derivative. Let's just do that. Let's confirm this rule by taking the derivative. So I don't know if I'd even call this a proof, but just confirming that it works. So we've got the rule is integral of x to the n dx is equal to x to the n plus 1 all over n plus 1 plus c. Let's take the derivative of this. And see if we get x to the n. Well, the derivative tells me to take this power and drop it down, so I'd have n plus 1. Got to wrap it in parentheses because it's more than one term here. Then over n plus 1 in the bottom. And then times x, and then the derivative tells me to drop this down by 1, like subtract 1 from it, but n plus 1 minus 1 is just n, and then the c goes away, right? But what am I left with here? N plus 1, whatever these are, they cancel each other because they're exactly the same. And I'm just left with x to the n, which is exactly what's under the integral there. Okay. Let's move on to sums, differences, and constant multiples. Now, if you remember from differentiation, basically these rules work exactly how you think they would. If I ask you to take the derivative of x squared plus 2x, then you just take the derivative of each term individually. And that's exactly how integration is going to work. If you've got the sum of two functions, just two functions of x, it could just be like e to the x plus 2x or something like that. If you've got a sum, then that's the same as each integral separate. F of x dx plus integral of g of x dx. Basically what I'm telling you here is that addition works exactly like you think it would. There's no special rule for addition or subtraction, and I can kind of condense those just like this. I'll say plus or minus and plus or minus. It's the same thing for a constant multiple. If I have like some number times a function of x, some number a times a function of x, I can just store that constant multiple out front just like I would do with a derivative, right? Just take the derivative of the function of x. Same thing here. Just take the integral of the function of x and attach that number back on in the end. Okay. By the way, if you take further math classes, all of these properties can be condensed in one, so you may see it this way. In fact, our textbook might even do it this way, where you have an integral of some function or some constant times your first function plus or minus some other constant times your second function dx is equal to, pull the a out of the first one and then f of x. This is just a way of saying both of these rules at once. So sometimes you might see it like this. But here it's split up into sums and differences and constant multiples. Here it's got everything all at once. We've got the sum and difference and two constant multiples. Okay, let's do some practice with those. Examples with sums, differences, and constant multiples. X cubed plus 1 dx. Okay, so we see here that we have a sum of two functions, x cubed and just the constant 1, so we can write this as two separate integrals, x cubed dx, integral of x cubed dx, plus integral of 1 dx. Using the power rule for each of these, we're getting x cubed, that's going to be x to the 4th over 4 plus c, plus, and we actually did this one earlier, this is kind of one of those tricky ones, but if it's just a constant, you basically just tack an x on, x plus, now we have two different constant terms here for after integrating, c1 and c2. But what we can actually say is they just kind of get absorbed into each other and we just end up with one constant. Because even if this is like a 7 and this is a 23, then the new constant would just be 30. It doesn't really matter as long as we have just one constant in the end. It doesn't matter how many constants end up here, how many different integrals we have to split into. They can all just be absorbed into one new constant real number. So let's try a constant multiple on the function being integrated. By the way, the function being integrated is called the integrand. I'll just say note. Function being integrated. So in this case, 5x cubed. the integrand. Okay, so we can write this, since we have a constant multiple inside, we can write it as 5 times the integral of x cubed dx. And then that 5 is just going to get carried along. I'm going to have 5 times x to the 4th over 4 by the power rule for x cubed plus c. And then I can distribute this 5, but again that c is that constant is gonna absorb that times 5, because if it's 6 here and I multiply by 5, it just becomes another real number. So I can just say 5 over 4 x to the 4th. It's multiplying the 5 by this first term, and then plus c, because that c can just absorb that times 5. Okay, let's do some more examples with sums and differences, etc. How about integral of 4x squared plus 6x minus 8 dx? So I can write this as, I'll write it here, integral of 4x squared, or how about this? Well, no, I'll do it one step at a time. 4x squared dx plus integral of 6x dx minus integral of 8 dx. Now I can apply the constant multiple rule and write this as 4 times integral of x squared dx plus 6 times integral of x dx minus 8 times integral of 1 dx. Okay. Now I'll apply the power rule to each one of these. So 4 times integral of x squared, but that's going to be x cubed over 3 by the power rule, and then plus c, say plus c1. and I know that this 4 does technically get multiplied by this constant, but it doesn't matter. It will just absorb, so I don't need parentheses there. Then plus 6 times the indefinite integral of x, so using the power rule again, the exponent is 1, so I'll add 1 and then divide by that, n plus 1. And then plus c2 for the constant from this integration. Then minus 8 times integral of 1, though, is just x plus the constant. And now I can contain all of these real number constants in just one term. So I'll say 4 over 3x cubed plus 3x squared minus 8x plus c. 4 over 3 coming from 4 times 1/3, so 4 over 3. Then 6 over 2 is 3, and then minus 8, and then all of these constants are just absorbed into 1. All right. How about integral of 5 e to the x dx? Well, I can write this as 5 times integral of e to the x dx, pulling that constant out. But the integral of e to the x is just e to the x plus a constant, so I've got 5 times e to the x plus a constant. There we go, that's it. E to the x is a very nicely behaved function. How about number 5, integral of 10x to the 4th plus 2x squared minus 3e to the x dx. So why don't I do this one a little bit quicker? I'm not going to split it, I'm not going to separate these rules of sums and differences and then constant multiples. I'm going to do it all at once. So I'll say this is the same as 10 times the integral of x to the 4th dx, there's the first term, plus 2 times the integral of x squared dx, there's the second term, minus 3 times the integral of e to the x dx. Now I'm ready to integrate each one of these. X to the 4th, I'll write my 10, I'll add 1 to the exponent, so x to the 5th, and then divide by that new exponent. Then plus, and by the way, I'm going to write all the constants for this integration, all these different integrations, I'm just going to write it at the end as a plus c, absorbing all 3 constants of integration into 1. So now my next one is going to be 2, and then x squared, so the exponent is 2, so I'll raise the exponent by 1 and then divide by that new exponent, and then minus 3e to the x, right? Because e to the x, integral of e to the x is just e to the x, and I'm just attaching that negative 3 to it. Finally, my constant at the end is plus c, and I can clean this up a little bit, because 10 over 5 up front here, 10 over 5 is 2, so 2x to the 5th, and then I can write this as 2/3 x cubed, and then minus 3e to the x, and then plus c. Okay. Let's do a couple more weird ones that same rules apply. Oh, actually, one more normal one and then 2 more weird ones. So number 6, integral of e to the x plus 3 to the x dx. Let me write those in parentheses. That's the same as integral of e to the x dx plus integral of 3 to the x dx. Now I cannot pull this 3 out because that's not a coefficient, right? That's not like 3 times x, it's 3 raised to the x. This 3 is a part of this function. I cannot remove the 3 and just have that x floating up there by itself. Okay. Wait a second. Well, we didn't actually officially define the integral for an exponential, but we did one earlier, so we can work off of that. Where was it? There it is. Integral of 2 to the x dx is equal to 1 over ln of the base times the original. So let me write that. Like this. Just off on the side here, integral of b to the x dx is equal to 1 over ln of b times b to the x plus c. The plus c just being the constant there. Okay, so right here from the first integral, we're just going to have e to the x. That's it. We're going to attach the constant at the end. And then plus integral of 3 to the x will be 1 over ln of 3 times 3 to the x, and then plus c. There we go. Alright, number 7. Number 7 is a weird one. Integral of 3e to the x minus 2 times 1.2 to the x plus 5, and then dx all the way on the outside. Okay, so if I write this as 3 separate integrals, I'm going to have 3 times the integral of e to the x dx. There's the first term, pulling that 3 out, minus 2 times integral of 1.2 to the x dx. See how the 1.2 is what x is raised to, so that stays inside the integral, but this minus 2 is a constant multiple. That can come out of the integral. And then plus 5 times the integral of 1 dx, or just integral of dx. I can write it that way. Now here I'm going to have 3e to the x. That's nice. Integral of e to the x is just e to the x. Then minus 2 times, now I'm going to use this rule here for integral of 1.2 to the x. So b is 1.2 here, so I'm going to have 1 over ln of 1.2, then times the original function, 1.2 to the x. So that's times, this is times, this is times, this is a decimal point. And then plus integral of just dx, or integral of just 1 dx, is x, so I'm going to have 5 times x, and then at the very end my plus c for my constants. And if I wanted to clean this up, I could write it as 3e to the x minus 2 over ln of 1.2 times 1.2 to the x plus 5x. Cleans up a little bit just putting that 2 up there. Okay, one more, and we'll move on to changing some variables, letter names, and then applications. Alright, number 8 for sums, differences, and constant multiples. This is a good one. Integral of 1 over x plus 1 over x squared dx. Well, this is a case where they're not written with their exponents explicitly stated, right? So I need to rewrite this integral as x to the negative 1 plus x to the negative 2. Okay, so that's just writing them with their negative exponents. And now I can't use the power rule, right? This is that special case. X to the negative 1 is that special case. So what I can do first, though, is go ahead and split that integral, like this, around the addition. And then again, x to the negative 1 is that special case that's equal to ln of absolute value of x. X to the negative 2, I can use the power rule on. The only function with x raised to a power, the only number that doesn't work is this negative 1. That's that special case. You just have to remember that integral of x to the negative 1 is equal to ln of absolute value of x. Now here n is negative 2, so I'm going to have plus x to the negative 1 over negative 1. Adding 1 to negative 2 gives me a negative 1, and that coefficient should match in the denominator here. This can clean up a little bit to ln of absolute value of x minus x to the negative 1 plus c, or if you wanted to write it as a rational function, ln of absolute value of x minus 1 over x plus c. Of course, the plus c is just that constant of integration that's carrying along. Okay. Let's say examples with different variables. These are just a couple examples just to show you that you can integrate things that are not functions of x. Like, what if it's t? Well, the only difference is the t, literally, you're just going to act like it's just an x. It doesn't matter. It doesn't matter. So, integral of t squared plus 14t. Let's see, can I skip the step of splitting the integral and just say integral of t squared is t cubed over 3, and then plus integral of 14t would be 14 times t squared over 2, and then plus c. Still use c for your constant. The only time you wouldn't use c for your constant is if you're integrating like a cost function where c is already being used. Then you could use k for your constant. Usually it's a capital letter. Now here, this can clean up a little bit. T cubed over 3 plus 7t squared plus c. And then one more with the letter u. We will actually be using the letter u a lot. In later sections. So what about 2u to the negative 4th plus u du? You see how I'm matching? If it's a u, I write du. If it's a t, I write dt. This little notation here, the letter attached to d, should match whatever the variable is for this function. Okay. So this is the same as 2 times u to the negative 3 over negative 3, just using the power rule there, adding 1 to the exponent, plus u squared over 2, and then plus c. And if I like, I can clean this up a bit. Negative 2/3, or actually u would be in the bottom, right? Negative 2/3 times u cubed in the bottom, and then plus u squared over 2 plus c. Okay. Next video is going to be applications of the indefinite integral.